Welcome to Ready to Derive. In this video, we're going to learn about the process of antidifferentiation, which is the reverse process of differentiation. They're kind of like inverse operations, almost, with a little tweak, in the same way that division is the inverse of multiplication and subtraction the inverse of addition. So it's kind of, we should appreciate the fact that we don't call subtraction anti-addition and we don't call division anti-multiplication. It's quite a mouthful. So we will learn about finding antiderivatives, which is the result of this process, and learn some important rules, important formulas you should know about antiderivatives. As always, we'll also have a large number of visuals to help us kind of make the concepts more concrete. So without further ado, let's get started. So let's begin with a scenario. Kind of a more visual approach to the concept of antidifferentiation. So here we have an object launched vertically into the air, has the velocity curve shown. And we are going to say that, so velocity right now is on the y-axis, time is on the x, and this is meters per second, and time is in seconds. So you can see from, for example, the y-intercept, that the initial velocity is 60 meters per second. And what we're going to start by doing is just recalling a skill we've worked on previously in previous videos. We're going to call this f prime, this graph f prime, and just kind of get rid of context for a moment and just think about, well, how would we sketch a graph of f given f prime? And we notice at x equals 6, f prime equals 0. So we must have a horizontal tangent line on f there. Prior to 6, f prime is above the x-axis, so it's positive. After 6, f prime is below the x-axis, so it's negative. And since f prime changes from positive to negative at x equals 6, we know that we have a local maximum by the first derivative test. So somewhere up here, we have a local maximum of f. But what information about the motion of the object does f give? Well, if f prime is velocity, that's the rate of change of distance with time, then that means that f must, or distance or height, f must represent the height with units of meters. So we know how to do the sketch. We don't know how, it's obviously an upside down parabola. We don't know how wide or thin. The other thing we really don't know is where to place that vertex, right? Because there's options. So there's kind of multiple graphs of f that could give the same f prime graph as its derivative. So let's work with this. So let's bring up that graph of velocity again. And we're going to approach this now using sort of more of an algebraic approach, get some calculus involved in here. So our first step is to write an equation for f prime x. And we see that in this equation, let's see, we see up here the 60 that's the y-intercept. We can also figure out the slope by just taking kind of two obvious points. It seems like we go down 20 units and across 2 using the units on the x and y axes, not counting boxes. So the slope is negative 20 over 2, which is negative 10. So using slope-intercept form, but I'm going to actually start with the y-intercept of 60 because it's good to think about that's its initial velocity, and then every second it's going to lose the slope, which is 10 meters per second. So that would be the equation for a linear function. That's not too bad. Now this is the conceptual leap. We are going to see, given that we know f prime x is this function, we're going to kind of try and work backwards and figure out, well, what must f of x have been in order that when we took its derivative, we got f prime x. So I'm hoping that you can see that to get the 60 here, that must have been, we must have had, the first term must have been 60x because the derivative of 60x is 60. So that one wasn't so bad. This might take a little more work. If we think about it, how can we get a derivative of a function that has x in it if it wasn't x squared to begin with? So bear with me here. Just this is experimental. We'll have a more sort of, a better procedure for approaching these moving forward. But I'm trying to think of what number should go here, that when I take the derivative, so when I multiply the 2 down to there, I get negative 10. And hoping that you see that it would have to be minus 5, because minus 5 times 2 would be negative 10x. By the power rule, we get back to that. So there's just one problem here, is though that in doing this process, it is possible that there was some sort of constant term there, that when we took the derivative, it disappeared. So there's some options here, and I am going to, let's see, for convenience, I'm going to just make up something and say, let's just pretend that number was 20. What does that do for us? Well, let's look at a sketch on Desmos of those two graphs. So this is f prime here, and this function up here is f. And we can see that the 20, so where does this 20 appear? That 20 is kind of locks the particular f graph into place. And so this is an example. So f is an example of an antiderivative of f prime. But you'll find out shortly that is not the only one. So let's just take a look at this kind of inverse relationship between differentiation and anti-differentiation. So if we take a function like the one we got in the last slide and we perform differentiation, I take the derivative, we get this. And the inverse process, the reverse process, is called, now we know, it's called antidifferentiation. But notice that antidifferentiation is it's not quite the perfect inverse, because we're not guaranteed that that number there is 20. We realize it could be other numbers. So we say that this particular example we came up with for what f of x could be is, we call it an antiderivative. And we achieve that in the process of antidifferentiation. But let's have a look at, it's not the only antiderivative as we saw before. So here's all the possible things, depending on what we made that value, whether it was 20 or 40 or 60, we could get a whole bunch of curves. And as you can see here, they're all parabolas, right? They're all quadratics. But as you can see here, in this case, we just pretended that was plus 0, 20, 40, 60. And what we call this is a family of antiderivatives. So they all kind of get associated with that derivative function, but you obviously need a little more information to be able to kind of lock into the particular antiderivative. So let's pause for a moment to create the definition of an antiderivative. In the previous slide, we used f prime x as our original function, and when we created the antiderivative, then that would be, we called it f of x. That makes sense, because the derivative of f of x is f prime. Well, what if we would like to just know the definition of an antiderivative of any function f of x? So the convention in calculus is to use uppercase f of x. That often represents the antiderivative. So that will help to explain this definition. A function f of x is called an antiderivative of little f of x if, obviously, if when you take the derivative of that function, you get back to little f of x. Since an antiderivative is not unique, as we saw in the previous example where we saw all those parabolas that could be possible antiderivatives of the original function, we define the general antiderivative to be this. So we just put plus c to allow for the fact that we don't know what that constant is, but we are aware of it. So, oh yes, where c is a constant. Okay, so one simple example before we get into, more practice, is if little f of x is equal to cosine x, then what is the antiderivative of cosine x? Well, what function, this is the way you have to think about these problems, what function, if you take the derivative of it, do you get back to cosine x? And if you recall, that was sine x. So you can always do a little check when you're trying to find antiderivatives. You could always think to yourself, well, let's see, if it's sine x, what is the derivative of sine x? It's cosine x. Check, that works. All right, so let's practice finding a general antiderivative of some power functions. In doing this, we should be able to derive a general formula for finding antiderivatives of power functions. And since this is ready to derive, this is what we love doing best. So here's the function, and this column is going to represent the antiderivative. And let's start with a simple problem. So the antiderivative of 4, we know from a practice problem before that this must be 4x, because the derivative of 4x is indeed 4. Okay, so what about the antiderivative of 4x? Well, we know that it must have come from, it must be an x squared. You take the derivative of x squared and you do get a term with x in it. The derivative of x squared would be 2x, but I want 4x. So if I just put a 2 there, then the derivative of 2x squared will indeed be 4x, and it works. Okay, so what about if we have 4x squared? This one needs a little extra attention here. So clearly it must have come from an x cubed function. I hope that you are noticing that whatever the exponent is, you just add 1 to get the new exponent. And I'm going to put the 4 aside for a moment, because the problem is the derivative of x cubed is 3x squared, and I don't see a single 3 there, so I don't want 3 in there. And the way you compensate for that is multiplying that by 1/3. So the derivative of 1/3 x cubed is just x squared, and then you have times 4. So this would be 4/3 x cubed. Now, I've already forgot to include the constant here, plus c. Learn from my mistakes that should always be included to be the general antiderivative. All right, we'll do one more of these, 4x cubed. So by the same reasoning as before, we add 1 to 3, so we know that the antiderivative should be of the order of x to the 4th. And now if we take the derivative of x to the 4th, we actually get 4x cubed directly, so we don't even have to mess around with coefficients. That one wasn't so bad, but it does appear that this probably one is the one we should focus in on. It was a little harder to get. So here's the general formula. So if f of x is a power function of that form, then the antiderivative, so notice what I said before. Remember, we took the n and we added 1. So whatever n is, you add 1 to it to get the new exponent. And to compensate for that, in the event that it doesn't divide evenly into a, you need to make sure that you are compensating for it by putting it in the denominator. And notice that the 4 is just the value of a to begin with. So, so this is the general formula. Now this only is true if n is not equal to -1. If n is equal to -1, so think about it, x to the -1, that's the same as 1 over x. There's a special rule for that one, and we'll learn about that shortly. So let's do one more practice. Here's a little box to make it look pretty. Let's do one more practice problem. Let's look at 4 rad x, because that's a power function in disguise. So that is 4x to the half. So by the rule that we just saw, a is 4. What we have to do is take the exponent of a half. Sorry, it's kind of really messy there. Let me just rewrite that. And we basically add 1 to it. And then we don't forget to put that down here also. So, and then we simplify. So x to the half plus 1 is 3/2. And the 3/2 on the bottom. And then we have to kind of do the keep change flip thing. And if you do that, you'll get 8/3 x to the 3/2. So let's create a list of antiderivatives you should know well. In these ones, I'm not going to put the plus c because it's just tedious to do so. If I don't put plus c, I'm sort of assuming c equals 0. So you might say that these are called particular antiderivatives. That's what you mean when you lock c into a certain value. But let's dive right in. So we just learned about x to the n. We just raise the exponent by 1. And we compensate that by putting 1 over n plus 1. Notice I have no a here. So this is just the simple form. N is not allowed to be -1. All right, why is n not allowed to be -1? Well, that would be x to the -1, which we realize is 1 over x. And if you recall, the function that had a derivative of 1 over x was actually ln x. Now, because in 1 over x, x could be negative, we compensate for that by putting an absolute value there. And we must always remember that x can't be 0 from the beginning, right? From 1 over x, it wasn't allowed to be 0. My favorite antiderivative, the derivative of e to the x is e to the x, and therefore so is the antiderivative. 2 to the x, or any base to the x that isn't e to the x. So if you recall, the derivative of 2 to the x was 2 to the x ln 2. So I can't just write 2 to the x here because I would get an ln 2 there that I didn't want. So of course, in the same way that when we got n plus 1 and we divided by n plus 1, you can kind of divide by that quantity ln 2. Just leave it there so that when you take the derivative, the ln 2's, which are constants, remember, they would cancel out. The antiderivative of sine x, well, we know cosine x and sine x kind of like interchange, but so I'm going to start with cosine x, but if you take the derivative of cosine x, you would get negative sine x. So to compensate for that, you put a negative in front of there, so the negatives would cancel out. The antiderivative of cosine x is nice. It's just sine x. The antiderivative of cosecant squared is cotangent, and again, we get some negatives involved in there, so let's compensate by putting the negative here. Secant squared x, the antiderivative, if you recall, the derivative of tan x is secant squared x. So look up those derivative formulas if you're having trouble remembering any of this. Cosecant x, cotangent x, the antiderivative is cosecant x. You need a negative there because you'll get a negative when you take the derivative. You need those to cancel out. And finally, secant x is there. There are other antiderivative formulas. We won't cover them here, but you could always look in your textbook and you could find all the antiderivatives you could ever hope to know. So let's have a little more practice of finding the general antiderivative of some functions. So here's one, and when we have sums or differences, we can always take the antiderivative of each term separately. That's kind of a law or a rule. In the same way you can do that for derivatives. But before we even do that, we first of all have to kind of separate it out. We don't have an antiderivative rule for quotients, so we need to rewrite this first as 6x squared plus 5. Only then can we get into finding the antiderivative, and we do that for each term separately. So, and the rule is, so we're dealing with power terms, so we can think about this. We would just add 1 to that exponent, so we know that there should be an x cubed there. We can let that 6 hang out for a moment and not forget to make sure we divide by that new exponent according to that rule. And then we have plus 5x and then plus a constant, don't forget. And you could simplify that down to make a 2 there. Okay, so the next one takes a little tweaking first. So let's first of all realize that this is a power function, t to the 1/3, but do not write this as 7t to the -1 because you might be fooled into thinking you can use that reverse power rule. Once again, we're going to add 1 to the exponent of the power, and 1 plus 1/3 is going to be 4/3. Now we could say, well then, let's see, multiply by 1 over 4/3. Notice that a is just 1. Or we could realize that, gosh, 1 over 4/3 is just the reciprocal. So why not write this as 3/4, save a little time, minus 7. The antiderivative of 1 over t would be ln of the absolute value of t plus a constant. And then one more example. Here we have to sort of get rid of the product situation, so let's distribute that. And minus 2 secant theta tan theta. And then it might help to make sure you refer back to the slide from the page before. Oh, by the way, you can always check your answers by differentiation. I'm not going to do that right now, but you can check these as you're going along. For this one, it's really the best way to do it. the antiderivative of secant squared we know is tan, and the antiderivative of secant tan is just secant. And that's a pretty straightforward one to, in terms of checking by differentiation. This one isn't hard to do at all. The others could be a little cumbersome, but it's always worth it if you have time. So hopefully you noticed that in the slide before, I left off the C for the third problem. I wish I could say that was intentional to sort of keep you on your toes, but it wasn't. So try to avoid my mistakes. All right, we're going to build a little on antiderivatives and learn how to find the antiderivative. So what does that mean? So you've given this graph of f prime. Notice that I'm not using little f and big F right now. I'm going back to f prime. The antiderivative of f prime would be represented by f. So sketch an antiderivative of f prime. So we see that f prime is 0 here, and it's going from negative to positive. So it must mean we have a local min right there. And f prime is 0 here, going from positive to negative, which must mean we have a local max. And so we've done this before. We're getting pretty good at it. This would be an antiderivative. Let's call that f. But we realized from before that you could also move this up and down because of the plus c. So what does it mean to sketch or find the antiderivative? So now if you're given this, you need to be given a piece of information in order to lock in one of those curves. So if you're told f of 0 equals 5, let's pretend this is 5. Then that locks this in, and we would then say that we have sketched the antiderivative of f prime with that condition. Let's look at some of the algebra. The blue curve is an upside down parabola, and I'm giving you this information that f of 0 equals 5. So let's do what we were doing before. Let's start by finding the antiderivative. So the squared would go up to a cube, and we have to divide by 3 to account for that. The exponent of x, that's 1, so that would have to go up 1, x squared. And to get back to 6x, we would need a 3 there to make that work. Minus 7x plus c. So normally we would have stopped there. That would be the general antiderivative. But now we know that f of 0 equals 5. We can actually plug this point in. So that means that 5 equals, if we plug x equals 0 in everywhere on the right hand side, we get 0 plus 0 minus 0 plus c. We actually get left with a value for c. c equals 5, and that gives us the antiderivative of f prime using that condition f of 0 equals 5. So for the last practice problem, we get to see that this process of antidifferentiation can happen kind of again and again. So in this case, we have f double prime, and we would like to find f of x, but now we have two conditions. We know that f prime of pi over 2 is 3, and f of pi equals 0, and we're going to work with both of those to reconstruct the original function f of x. So let's just bring this down here to cosine x, and the first step, of course, is to take the antiderivative, which will bring us to f prime. So the antiderivative of cosine x is sine x, but we mustn't forget that plus c. Now, at this point, we have to find c by plugging in the point that we have that can help. So we know that f prime of pi over 2 is 3. So we just plug this into our equation. We get 3 equals 2 sine pi over 2 plus c. So that's sine pi over 2 is 1. So that delivers us that c equals 1. So now we have a full formula for f prime x. So let's just write that out. It's very important to write it out with the value of c in. Okay, so this is kind of a interim equation that's very important. And now we just repeat. So the antiderivative of f prime, f of x. Now the antiderivative sign, don't forget, is negative cosine. So it's going to become negative 2 cosine x, and the antiderivative of 1 is x. And now we mustn't forget plus c. Sometimes you could call it plus d or whatever you would like, but every time c is a different value, so we tend to just use c. Now we need to plug in the point that will help us solve for c. So f of prime equals 0. So that means f of pi equals 0, negative 2 cosine pi plus c, and that should all equal 0. And cosine pi is negative 1, so that means 0 equals 2 plus pi plus c. So c in this case is negative 2 minus pi. So that brings us to the final answer. We've completely reconstructed f of x, and it's negative 2 cosine x plus x minus pi minus 2. And that brings us to the end of this lesson. I hope you found it helpful, and if you did, please do click like and/or subscribe to my YouTube channel, Ready to Derive. Thank you.